Let's talk about memory management for cloud functions, a topic of interest if you want to further continue the paradigm of serverless computing. My name is Josef Spillner. I'm from Zurich University of Applied Sciences, and I would like to introduce to you the issues concerning provisioning and billing of resources for serverless computing under a utility computing model, where we are concerned with shortening the billing cycles from hours and minutes to seconds and subseconds, as well as making more fine-grained memory allocations in individual megabyte steps or even below. As researchers, we have conducted several experiments to shorten the amount of wasted time and to reduce the amount of wasted memory allocations. You find the GitHub links, so please look at those links if you want to get more information, if you want to try out certain tools. The way it looks like is that we typically are charged by a product of duration of the function execution and the memory allocation, and the memory allocation is static. It's occurring all of the time, despite the fact that the application, in particular all of the functions which are executed, typically require a more dynamic profile. They do not necessarily require all of the memory all of the time. So in order to reduce the waste, we could look at three potential limitations to overcome. The first one is an economic one. Currently, most cloud providers only offer coarse-grained memory steppings. There is no inherent technical reason for that. Therefore, we can look at reducing the stepping size. The second one is overcoming the static memory allocation, which in some isolation technologies such as Docker has been implemented. In more recent versions, we have the ability to tune memory automatically. But even if the underlying isolation technology in the cloud provider allows for tuning the memory allocation, the second part of this second step here is to look for a pass-through of these options for the API, and this is currently not the case for any of the cloud providers offering function as a service. And the third one is that there are no tracing tools available, no tools that suggest to users to optimize their memory allocation. For example, if they over provision memory in the configuration file statically, it is rather trivial to find out that they could reduce, because in 99% or even 100% of occurrences, only half of the memory is actually used. There are a typical set of isolation technologies in use by the cloud provider. So if we look at process level isolation, where we have almost no isolation, we also don't have the memory issues. Therefore, we are looking more closely at containers, which have been from the very start of serverless computing a technology where the isolation level is good enough for most cases, but we had the issue of static boundaries. And of course, more recently, serverless offerings have been isolated with different technologies, such as Firecracker, which have other possibilities. In particular, memory ballooning has been implemented for hypervisors for a long time. There are new isolation technologies coming up. There's a lot of recent research on WebAssembly, and we also see renewed interest by researchers on vertical scalability, as horizontal scalability, the dominant scalability paradigm in cloud computing, by itself is no longer sufficient. So if we look at the characteristics of FaaS providers, we see a number of characteristics which are often not available to be processed in machine-readable form, but we retrieve that from websites, we find that in documentation, or we find that as dark knowledge by experts discussing on forums or directly looking into the code of certain applications, circumventing or bypassing certain restrictions in serverless with workarounds. And from that, what we did was deriving tabular representation, as you can see below, of all of the constraints, and that includes memory allocation constraints, so that we have something systematic that we can exploit at runtime to find out which memory allocations are permitted. We have turned that into a knowledge base called the FaaS characteristics and constraints knowledge base, which is published on several open data sites. So again, we have a GitHub link for you to download the latest version. Now, if you look at the memory runtime aspects, what we did was creating a tracing tool, first working on local Docker containers. That equally applies to Dockerized function execution in higher level cloud platforms, such as if you run Fission on top of Kubernetes. And you get a trace profile similar to what is shown on the right side, with relatively small tracing periods. So it is quite suitable for getting information that would allow for adjusting the memory allocation in less than 100 millisecond intervals, which is quite sufficient to fit into most serverless provisioning and billing models. If the cloud function is not running in a local Docker container, but is executed in a remote FaaS service, we need to retrieve monitoring metrics, especially memory usage metrics, from the appropriate APIs. We see there are certain restrictions, such as what is shown here for Google Cloud Functions. We only get samples every 60 seconds, and there is a delay period of up to 240 seconds, which is, of course, not very suitable for functions which are only running for a few seconds. What we did was further creating a consumption model. We derived a model including a workflow where we said we would look at the function-based application, which is running in containers or in other serverless environments. We would have a dedicated tool to calculate memory traces, to fetch them and aggregate them. And in the next step, we would like to apply such a profile to a certain FaaS engine. That could be a static allocation, as is the case in most current FaaS runtimes, or it could be a dynamic one, such as a future runtime that allows adjusting the memory allocation at runtime. What we did specifically was gathering a lot of the individual memory traces, calculating the outer hull, which is shown as a black line here. From that, deriving the upscaling hull with a bit of a safety buffer, so taking into account that adding additional memory in vertical scaling models will take some amount of time, and then looking at which memory gains were achieved, which are the differences between the blue and dashed orange line, and which time savings were potentially achieved between the green and the dashed red line. If we look at two concrete trace profiles, we see the same cloud function called futil/resize being applied on the one hand to the same picture. So we see that most of the trace lines are relatively similar, and also applied to pictures of different sizes. So we can see that depending on the input data, we get a different trace profile. A small one, a medium one, and a large picture has been resized here. And so from that, we derived certain methods how we can determine input profiles. Even though that was not the center of the research, we have some proposals how we can determine upfront which profiles we have, and then have memory allocation upscaling depending on the profile which applies in a certain case. Finally, we suggest that next generation FaaS engines and APIs allow for setting memory dynamically, for instance, by simply specifying a trace profile at the very beginning, or even by deep tracing the memory allocation by associating the need for certain memory to associated events that happen in the on the code level. We see that with fine-grained static allocation, we typically save between 0 and 50%. The case you see here is that the saving is 0 because we require precisely 768 megabytes of memory, which is something we could as well configure in most of the FaaS providers. However, dynamic allocation, which is then the gray curve shown here, allows us to save a lot more, up to 90% of the memory needs. There are a couple of caveats, like the initial allocation period. Initially, the cloud function should be provided with an infinitive amount of memory. The sampling rate, which is shown here with the duration of these intervals, and a couple of safety buffers. So in case the upscaling takes longer, we may want to left shift the gray curve. And in case the measurements are not very precise or there are some deviations, we would like to upshift it. Thank you for listening.